We interact with these massive AI models all the time, right? And they just seem to know stuff, an incredible amount of stuff. But if you ever really stop to think about it, how does an AI actually know a fact? Where, inside all those circuits and code, is the knowledge actually stored? Well, today we're going to peel back the layers and take a look. Okay, so let's make this super concrete. You go to an LLM, you type in Michael Jordan plays the sport of, and boom, it spits out basketball without a moment's hesitation. It really does feel like magic, but it's not. Somewhere, deep inside that huge network of artificial neurons, that specific piece of information exists. So our mission today, we're going to go find it. All right, so where do we even start looking? To find a fact, you've got to go inside the machine itself. We need to understand how these things are built and where a little nugget of information like this could possibly be hiding. And hey, we're not just taking wild guesses here. This whole deep dive is based on some really fascinating research from Google DeepMind. They decided to tackle this exact problem, and they even use the same kind of example, matching famous athletes to their sports, to try and pinpoint where all this factual knowledge is actually stored. So their investigation led them to one prime suspect, a really specific and, as it turns out, absolutely critical part of the whole neural network. So let's meet our main character, the multi-layer perceptron, or as we'll call it, the MLP. Now, to get why the MLP is so important, you just need a quick peek at the transformer architecture. That's the engine behind models like GPT. It's really got two main parts. You've got the attention blocks, and their job is to figure out how all the words in a sentence relate to each other, for context. And then you have the MLP blocks. Think of them as doing their own little computations on each word, one by one. The big question for the researchers was simple. Which one of these is doing all the heavy lifting when it comes to storing facts? And this is where it gets really, really interesting. Take a look at the breakdown for a model like GPT-3. The MLPs aren't just some component. They are pretty much the whole show. We're talking about 2/3 of the entire model's parameters. It's just overwhelmingly MLP. And this number just drives the point home. That 2/3 chunk, it translates to a mind-boggling 116 billion parameters. That's 116 billion tiny little knobs the model can tweak, and they're all packed inside these MLP blocks. I mean, if you're looking for where memories are stored, you're going to start in the place with the most real estate, right? Okay, so we've found the neighborhood where the facts probably live. But what's the actual mechanism here? How does an MLP see the name Michael Jordan and somehow connect it to the word basketball? So, the key idea here is to stop thinking about words as just text. Instead, imagine every single concept, Michael, Jordan, basketball, you name it, is a specific point on a massive invisible map. In the AI's high-dimensional world, every idea has a location, and the relationship between them is like a direction or a vector in this crazy mathematical space. With that map idea in our heads, we can actually break down how a fact gets recalled into a pretty simple 3-step process. First, the model's got to detect the subject. Then, it needs to activate a neuron. And finally, it can add the fact. Let's walk through it real quick. Step 1 is all about detection. You can think of a little piece of the MLP as being a highly specialized detector. Through some math, a matrix multiplication, it's basically asking the incoming data one simple question. Hey, are you the concept of Michael Jordan? If the data lines up just right with what it's looking for, it spits out a nice high score. But, a raw score can be kinda messy. So to clean things up, the model uses this brilliantly simple little tool. It's called a ReLU, and its job is just beautiful in its simplicity. If a number is positive, it lets it pass right through. If it's negative, it just flattens it to 0. That's it. So that ReLU acts like a perfect on-off switch. This is step 2, activate. It takes that score from our detector, and if it's high enough to be positive, bam, the neuron activates. If not, it's off. It becomes a clean signal, kind of like an AND gate in classic computing that only fires when it sees Michael and Jordan together. And that brings us to step 3, add the fact. Once that specific neuron is activated, it triggers a second mechanism. And this part is basically preloaded with a payload. In our case, when it's triggered, it just adds the direction for basketball to the final output. So the detection of Michael Jordan has now directly caused the retrieval of basketball. Pretty cool, right? So is that all there is to it?
Is a huge AI model just a giant collection of these simple little if-then switches? Well, that model we just went through was a great way to get the basic idea. But the reality, the reality is way weirder and honestly a lot more interesting.
I mean, it leads to the really obvious question, doesn't it? Is there literally one neuron for one fact? Is there a Michael Jordan neuron sitting next to the Eiffel Tower is in Paris neuron? And the answer seems to be a resounding no. The evidence suggests that this clean, one-to-one mapping is actually pretty rare. The real storage system is much stranger, and as we're about to see, it's also unbelievably more efficient. This brings us to a mind-bending idea called superposition. The theory goes that instead of storing one fact in one neuron, the model stores concepts across combinations of neurons. The best way to think about it is like laying multiple transparent pictures on top of each other. A whole bunch of different ideas can actually occupy the same space because they're superimposed. Now, that sounds totally impossible in our 3D world, right? To keep three ideas separate, you need length, width, and height. You run out of room really fast. But in the crazy high-dimensional space where an AI lives, you can pack in an exponentially larger number of ideas that are, well, almost separate. They're not perfectly distinct, but they're close enough that they don't really interfere with each other.
And this quote from the research really just hammers the point home. The storage capacity doesn't just grow linearly, it grows exponentially. A small bump in the number of dimensions gives you a colossal increase in how many concepts the model can cram in there efficiently. Okay, I know, that was a pretty deep dive into some seriously mind-bending ideas. So what's the big takeaway from all this? Why does this bizarre, overlapping storage system even matter in the real world? So here's the bottom line. Facts inside an AI aren't like files on your computer, stored neatly in one folder. They exist as these distributed, overlapping patterns spread across huge groups of neurons. This whole superposition trick is what makes these models so incredibly dense and efficient with information. And it really helps explain those emergent properties we keep hearing about, why just making a model bigger can suddenly unlock these shocking new abilities out of nowhere. And all of this leaves us with one last big question to chew on. If a fact isn't some single, solid thing you can retrieve, but instead it's this fuzzy, distributed pattern that gets reassembled every time, what does it even mean for an AI to know something? It kind of challenges our whole definition of what knowledge even is. Something to think about for sure.